Okay, so good morning, and we will continue our discussion on the Ising model. And you might wonder why I'm spending so much time on this model. And the main reason is that this is a very simple model, and it illustrates non-trivial ideas in the theory of phase transitions. And we'll also see in a few lectures later that there is a sense in which even the real gases have a similar behavior as this magnetic system. Okay, and that's like very counterintuitive, and we will see this idea of universality in phase transitions. And so there is a sense in which the para-ferro transition as well as the liquid gas transition are similar. Okay, so with that in mind, let's go back. Okay, so let us resume a study of the Ising model with the magnetic field. Okay, and so the equation that we needed to solve, and I keep writing 2m, that's because that should map to the normal variables. I mean, the way my lecture went, I ended up defining m with sigma, with being taking values plus or minus half instead of the standard plus or minus 1. So, okay, and so this was the consistency condition, which we solve for B. For not B, 2n, for 2n. Okay, so what I tried to do was said, so we, so, and, the thing is there was issue of stability, etc. And what I said is that this condition can be obtained as the extremum of a function I kept calling it free energy, but and without saying why it is the free energy, but actually you can. There is a sense in which it is indeed the free energy. Okay, it's a kind of free energy. Extremum of a function which I wrote as f of m or 2m actually, f of 2m. Okay, that I called the free energy. And we worked out what this f of m would be in the limit where 2m was small, b was small, etc. We had worked out some terms. There was a slight sign error, I think, in what I wrote yesterday. So, but actually, you can ask, can we write f of m for this full? Can we write the exact f of m, which where I don't need to make any approximations? And exercise, okay, show that f of m equal to minus t, okay, log of cos hyperbolic of whatever is that thing which went in the thing. So Tc by T upon 2m plus beta b by 2. Okay, plus okay Tc times 2m whole square by 2. Okay, so you just go ahead and just work out, take the derivative of this, and you should check that it gives you this thing. So, but it's like, it's like an integration. So you can see that 2m, if you integrate 2m, you'll get 2m squared by 2. And there is this prefactors in front. There's a t and a tc. You may even want to multiply it by a kb if you want f to have dimensions of energy. Okay, I didn't do that. Okay, so this is the structure. And okay, and but for By the way, this holds for not just, I mean, there's no condition on m being small, no condition on t being less than tc, etc. Okay, so then, but we also we saw, so we try to for t close to tc and 2m being small, then what else? Okay, b also to be small, so you can say that beta b by 2 or whatever. Instead of beta, I can write beta c. Okay, it's also much less than 1. So in this sort of approximation, we can write f as sum of two terms, f naught of m, okay, plus a term linear in b. Okay, plus there are of course higher order terms. So I'll just write ellipsis for all those things. Okay, so this is what the thing is, f naught of 2m again. Okay, so now if you go back and check what this f naught of 2m is, I'm just rewriting, putting all the things together which we had done before, and okay, so f naught is the free energy when b is 0. Okay, and for of course small values, so there's some truncations involved, and you can just okay, so this is a quartic, right? And the linear term in b is just okay. So I'm just rewriting formulae which we have worked out, etc. I think last lecture I didn't have this minus sign. That's the only error. Okay. And so I probably was looking at the cubic term, but let me look at I should actually be looking at the linear term. Okay, so but cubic term also has similar behavior, so it doesn't matter. But we'll look at the linear term. Okay, so which is this way, and so. Oh, okay. Oh boy. No, my graph which I wanted got moved. Several. Okay, so we have this picture. So we said keep t less than tc. Okay, so f of 2m versus 2m maybe, doesn't matter. Okay, so what we had was and b is 0. So I should write f naught if you want. Okay, so there were 3 extrema. Okay, and these two are equal. Now comes the thing when b greater than 0. Okay, so I'll draw a graph where I'll keep shifting. I might add constants to the free energy so that the minimum is at 0. So then what happens is that you get something. Okay, so you can see that this is the true minimum, global minimum. And this is just a local minimum. And if you take b sufficiently large, actually it should go away, but that's not the thing. And the last picture is when b is less than 0, then the thing gets lifted the other way. And so now this will be this value becomes the global minimum, and this is just a local minimum. Okay. Again, if B becomes larger, these two, what will happen is these two will come together and it will go off, and then there'll be just exactly one. I mean, there won't be, even the local minimum will go away for large enough B. Okay. So is this picture? Are these three pictures clear? And all this intuition we got by looking at for small values, etc. And you can also exercise this compute f value of metastable, the difference of these two guys. Okay, let's call these guys m naught and minus m naught at 2m naught minus 2m naught. No, I shouldn't give the value because it depends on b. You compare these things and you can check that this thing is proportional to b plus, of course, there are higher order terms. Okay, so please compute this for small values. Is this clear? Okay, so are there any comments, etc.? Okay, so let me try to move this guy. Can I move it? If I can't, it's okay. Okay, so now, so here, this is a plot. You can see this, right? Okay, so let's see if I can write on top of this. Okay, so there are three curves here. Okay, the blue curve, maybe it's not a good idea to write on top. Okay, so here, blue curve is b equal to 0. Okay, green is b less than 0, and what's the other color? Green. Okay, and orange is b greater than 0. Okay, I've done some shifting, but this is the exact f of a. So what I plotted here is not the truncated guy, and this shows that whatever picture that we had by assuming b is very small and we are very, very close, I mean, this is still t less than tc, but so this is what you get. Okay, so the pictures that I drew don't get changed much. You can see that this is for the exact function. Okay, so this is rather exact formula. What am I writing? I'm writing wrong thing. Okay, so this is a plot. Okay, so we have to live with that being there. So we just saw that the picture that we obtained, assuming that b was small, doesn't go away even if we use the exact free energy, because we have an expression. Quite often you cannot, okay? And that's a beautiful story involving renormalization, etc., which says why it's enough up to go up to quartic terms. So it involves something called renormalization, and it shows that the other higher order terms are irrelevant, and so they don't mess up the physics that you get from this Nile picture. Okay, so now I'll again draw one more picture which we have seen before, but this will be now M versus B. Okay, so you get something like this. So asymptotic value is half. On this side you will get. Okay. So this is the full, this is the exact this thing. But the point is that there is metastable, guys. Okay, so this is the, what do you call the, so you can check all these things, and I really want you to go back and look carefully and work this out. Okay. Another exercise for you. Okay. So for large V, okay, you should there should be a unique vacuum. Unique ground state, or I don't call it ground state, unique solution for 2n, and the potential and the free energy should look like this. Unique. Okay. So we can now, we are ready to draw the phase diagram, and this is so what is the phase diagram? There are two parameters, temperature and magnetic field, so T and B, and there's DC here. Okay, so the thing is that there are three phases. Okay, and first phase is M equal to 0. Second phase is M greater than 0. Third phase is M less than 0. Okay, so this is a paraphase. This is a ferrophase. So is this. Okay, so in this setup, so this is all spin up phase. In this region, M is greater than 0. In this region, M is less than 0, B is negative. Okay, and in this region, M equal to 0. So you see that there are three phases. And one more thing we know is that when we go at B equal to 0, there's a discontinuous jump in magnetization. So we have a first order transition here. And here, this is of course second order. So let's write that. But that is a T equal to Tc, B equal to 0. This much we have checked. Of course, from here to when you go from, so if you fix say B greater than 0 and go like this, somewhere you will reach a point where you will hit, m equal to 0. So I'm not showing that region. So far away here is the para region. So so we have three regions. So let's pop them. And these are the three phases. Okay. So now I'm going to give an analogy with liquid gas. Okay, so what is the analogy? The thing is, so for instance, water is not a good example, but it's okay. So we have water goes to steam. Okay, at standard conditions, T equal to 100 C, right? Okay, so if we keep water at 100 centigrade, the point is, will it? So for it to go to steam, you need to give some extra energy. Do you know what that extra energy is? Yeah. Okay. So what it says is that the internal, so the U of water, other way around. Okay. So and so we are in a canonical ensemble. So what kind of phase transition is this? So what does this mean? That the internal energy has a discontinuity, right? And if you are in the canonical ensemble, internal energy is how many derivatives of the free energy? Two. No, it's just one derivative. I mean, simplest way to understand is df by d beta is d log z by d beta. So you have to put in some factors, but it involves both the first and the second. It's a first order phase transition. Okay. So now the question is, how does what is the analog of man m? Okay, so see what happened was we'll call it the order parameter because its value tells you something. So coming back to this picture, so here we saw that there were three phases. One which is a paramagnetic phase where m was 0. Second was m greater than 0 and m less than 0. Okay, so these were three distinct phases, and so so the question is, what would be is there something which you can measure which will signal that there is a phase transition if you're measuring something? Okay, so in this case, so I'll give the answer because you people have been extremely silent, and so much so that I'm doubting if there's a connection. The answer is that the density, number density, is the analog. So you know that the density of water is different from the density of, for instance, is different from the density of steam, right? And so so in some sense, so all this stuff looks pretty much like you're going from here to here if you're crossing here. But if you crossed at this point, okay, then so one more thing is you can work out, even in this case, you can work out what is the difference. So I asked you to work out the difference in the free energies. Okay, if you work out the difference in the free energies as you approach TC, what should happen? What should happen to the difference? It'll start going to zero. So the discontinuity that you had goes away. Okay. So yeah. So similar to when T was equal to Tc rather than T. Okay. Similar when T equal to Tc. Here we have a similar situation where if you tune parameters, okay, so it could be temperature and pressure or volume, something you can do. You can tune parameters. Okay, we'll discuss this in more detail. The latent heat goes to zero. Okay. So one usually draws a P. Okay, so what one has is that maybe in the PT, P and T. Okay, so there will be some. I won't plot the rest of the diagram. So this side, this will be liquid, I guess, and this will be steam, gas. So there'll be a sequence of this thing. It'll end like this. Okay, and so yeah, so this will be first order, and this will be second order. So it depends on, yeah. So what you're keeping. So usually we have pressure. We don't change. We change temperature or whatever. So you can see that if you go, so as you come like this, you will cut this curve. So I'm keeping pressure fixed and I'm changing this thing. So if I cross at this point, I'll have some latent heat. But if I change, like you said, if I increase pressure such that it goes through this point, then you will not. There'll be no latent heat required. Okay, so that's the point. And yeah, so one more interesting thing is that you can go from gas to liquid. You can go without. You can come. So you can go. You can take paths like this. I'll draw something and erase it. So we can start from here, and if we can tune things, we can go like this. Okay. So you will see nothing happening. You will peacefully go from gas phase to the liquid phase, and you would never see the need for some latent heat or anything like that. Okay. So this is something which is interesting. Okay, so this is the so this is the analogy which is there, but actually the analogy is much more stronger. And so now I will discuss order parameters. So this will set us up for what we want to discuss. Next, we'll come back to how we will model the liquid gas thing, etc. So okay, so so we'll start with some abstract nonsense, and then but we should have basically our Ising model idea in mind. So we have some system that has multiple phase transition, has multiple phases, and undergoes various. Okay, so the idea is that so we need to look for some observable or measurable, but I'll just call it observable. Okay, that can tell you which phase you are in. Okay. We call that an order parameter. Okay, so examples. Okay, so Ising model. Okay, this would be just M, the average magnetization. Okay, 2 would be if you have interacting spin systems, the Heisenberg model. So we started off from the Heisenberg model and made some caricatures. So something like this: Si dot Sj, minus J, I J nearest neighbors. This kind of interaction. Okay. So here the order parameter will be a vector order parameter, which would be expectation value of S kind of thing. Okay, so vector order parameter. Here it's a scalar. Liquid gas is just number density. Okay, again it's a scalar order parameter. So okay, so this is the whole thing that if you follow these guys, you can tell which phase they are in. Okay, so again in the Heisenberg model, I mean you can see that S can take a continuum set of values. It's not like it's a vector. So it can take its magnitude might be, you might fix it, will be one scalar order parameter, but there'll be also directions. So there'll be a continuum. So there are many, many more examples, but these are the things. Okay. So what one does is to model these guys. One writes a free energy okay, that is a function of the order parameter as well as all other control parameters. Temperature, maybe the pressure, magnetic field. Okay, and of this order parameter, and then the minima these order parameters of the minimum of the free energy uh, will determine the phases, issues of stability, etc. So this is a method which is due to Landau and Ginsburg. And so the thing is, so of course, the key question is to determine this free energy, like we did in the Ising model, right? This is the key. How do we determine this free energy? How does it depend on parameters? Okay, so generally, it is pretty hard to write out the free energy explicitly as we did. The mean free solution. Okay, but however, uh, we can write of the quartic potential that we wrote, right? The quartic potential, quartic function, rather. In many cases. Okay, again. Okay, so the key input will be how the coefficients depend on the control variables, or I call them parameters here. I use the word parameters, so let's use the same thing. Okay, so the idea is that you can even do this by looking at the experiment, okay, saying, okay, so you have some experimental data, this is what it says, and you can try to, you can put it into the thing. So for instance, let's just remember, so let's look at f naught of 2m. Okay, so it had something like this, 2m power 4 by 12. Okay. This was the behavior for t less than tc. And so you can see that the parameter, so what we have is that the only parameter for when there's no magnetic field is temperature. And of course, there were some various things, t by tc power square, etc. If you notice, I throw them all away because the only thing that matters is that this guy, there is some dependence on this thing. Okay. So, but now I could have a situation where this dependence, so this is a specific dependence on temperature, okay, as of course close to Tc, which is a phase transition. But if you think a little bit, even if instead of having 1 minus T by Tc, if I had 1 minus t by tc power something here, some positive power, it will still have the same setup. But then what will happen is that that how things go to zero. So for instance, we saw that what did we see? We saw that m of t went as tc. Let's write it this way. Okay, so this one here and this being half, these are, so this is like an exponent. So okay, so the critical exponents such as beta depend crucially on how the parameters or the coefficients rather such as okay, so suppose we had a situation for where rho is some liquid gas density, number density, and it has this thing, it has a structure. I mean, the overall factors don't matter. Okay, then what will happen is that rho, what can you say about rho then? How will rho of t behave as t goes towards tc? So I have to be a little careful. So here rho could be a rho, instead of rho, I should use actually some rho minus rho naught or something. So I'll fix that by putting tildes here. Okay, so rho tilde is the difference, if you wish, it is the difference, but let's say it is rho minus, say, rho gas. What is it I want? I want for t less than tc to be liquid, yes. Then I want it to go to 0. I hope you get the idea. What I'm trying to say is here, if I did this thing, so then if you look at the calculation, will be identical. So what you will see is that rho tilde, okay, of t will have the same behavior, and it will, well, how should it go? It will go like 1 by t by tc power. The computation will be more or less the same. Okay, so and the claim here is that actually the liquid gas phase transition is identical to this. So okay, so what we are saying is, so here, so if what I'm saying is true, happens to be, then the exponents of the liquid gas phase transition I've given only one example, same as Ising model. Okay, so this would be the kind of prediction. Okay, and so this has a term. This is called universality. Okay, so the claim is the liquid gas, and you write it like this: phase transition is in the same universality class as the three-dimensional Ising model. Okay, I'm being very careful here because whatever this half here is what we call the mean field exponential. It didn't know anything about dimension, right? All dimensions disappeared because that's buried in the TC. Coordination number only came, but we know, as we will see in next lecture, that the mean field is not good in this thing. But I think from three it's pretty good. I think 3 or 4 onwards is definitely mean field is true. But this is the claim. Okay. So if you knew how to do, if you could compute the exponents of the Ising model, which people know how to do using, there's no exact solution, but people can get any exponent to pretty good accuracy using computers, Monte Carlo simulations. And then that happens to agree with this thing. Okay, so this is the claim. So this idea of universality is, okay, so of course, coming back to this problem, there is no way, the Heisenberg model will be in the same universality class as the Ising model. Why is that? Am I connected with you people, or it's gone? Connection is... I am, okay. So I claim that in this thing, I said 1 and 2 are equivalent, but I'm saying that 2 and 3 cannot be. And in part because if you look at it, the kind of order parameter is completely different. One, it's like a vector worth of parameters. So it's a very different system. And there's no reason for this to have this thing. But in these two cases, both of them at least have a scalar, in some sense, a scalar order parameter. And so there is some chance of this happening. Okay. So quite often, so in modeling phase transitions, it is often enough to understand the universality class. Lots of words, okay, today, very few equations, but these are these kind of ideas, and so they're abstract, but actually very, very powerful and very, very useful. And of course, you can never do justice to it in a first course in statistical mechanics, but if you do a second course, definitely you will encounter a lot of these things. Okay, but what I'm trying to tell you is that two disparate systems, one is a magnetic system, the other is a liquid gas system, fluids. Okay, so there, I mean, the a priori there is no reason why they should even be related, and actually they are. Okay, and so that's the whole thing. And so what we will do, there are things to do. So yes, first one is exact solution to the d equal to 1 Ising model, and I also need to do something like symmetry breaking. And the last bit which I want to do in phase transitions is real gases. Okay, this I don't know how I want to do this, but other two things I do have a very good idea of how I want to proceed. And So maybe I will just spend maybe 10 minutes on item 2, but we will spend some time on maybe a couple of lectures on real gases. Okay, so the key point here is that an ideal gas will never ever undergo a phase transition. Okay, it will remain a gas. Okay, so for all temperatures. And so we need something, we need interactions which will make them become liquids. Okay, and how do we put those interactions in, and what happens, etc. We can go ahead and we'll study that. Okay, so I'm done for today. I'll pause for questions.